Viewers, in the previous lecture we have discussed the assumptions of kinetic gas theory. Those were the volume of an individual gas molecule is negligible, then the collision between them was elastic and the pressure exerted by the container is only due to bombardment on the wall of the container. And the last assumption was the kinetic energy is directly proportional to the absolute temperature. After that, we derived the kinetic gas equation, that was PV is equal 1 by 3 mn V square. Here P stands for pressure exerted by the wall, V stands for the volume of the gas, m was the mass of the molecule, n the number of molecules of gas, V square was mean square velocity. And after that we did the difference between the ideal gas and real gas, because the kinetic gas equation followed by only ideal gas, not by real gas. So, we did the comparative study between the ideal gas and real gas. Ideal gas are known as ideal because they strictly follow Boyle's and Charles' law at all conditions of temperature and pressure. But non-ideal gases or real gases, they do not follow these rules at all conditions of temperature and pressure. Now, in this lecture plan, we are going to discuss the reasons of deviation of real gases from ideality character, the corrections in ideal gas equation suggested by van der Waals. Then we will derive the van der Waals equation. After that, we will discuss the significance of van der Waals constant. The real gases deviate from ideal character. Real gases do not follow ideal gas equation. The ideal gas equation is PV is equal nRT. The ideal gas equation is based upon number of assumptions. It is based upon kinetic theory of gases. So, the real gases are not following ideal gas equation. It means there should be some change, there are some incorrect assumptions. The van der Waals equation, which will reproduce more satisfactorily the PVT relations of gases. In 1873, J.D. van der Waal modified the ideal gas equation by adding some correction terms in it. He removed the two assumptions of kinetic theory of gases. The first assumption is the volume of an individual molecule is neglected in comparison to the total volume. Second assumption is the force of attraction between the molecules are neglected. So, these two assumptions are true, but if the distance between the gas molecule is large, and this is possible only in two conditions. First, if the pressure is low, and second, if the temperature is high. But the distance between the gas molecule is very less when they come closer. The conditions are at high pressure and at low temperature. At high pressure and low temperature, the volume occupied by the gas molecule is, it means, not negligible as compared to the total volume of the gas, since the volume occupied by the gas itself is small. It is visible from this graph that at low temperature there is maximum variation. The compressibility factor for real gas is less than 1, while in case of this gas. At high pressure, the variation is too much, they are showing maximum deviation, the value of compressibility factor is greater than unity. So, gases can be liquefied under high pressure, and it shows that the molecule of a gas has certain volume, and when the compressed gas is passed through the porous plug under adiabatic conditions, a thermal effect, a cooling effect was observed. It means there is some work is done against the force of attraction, as it is visible from here. This is Joule-Thomson effect. When a gas is compressed under adiabatic condition from this through this porous plug, there is thermal effect is seen. There is cooling effect, the temperature T2 is less than T1. It indicates that there is some work is done against the force of attraction between the molecules. So, now there are two changes in the assumptions of kinetic theory of gases. First change is the forces of attraction or repulsion between the gas molecule may not be negligible. So, we are going to do some corrections here. The intermolecular force of attraction increases with a decrease in distance between neighboring molecules, and thus pressure exerted by the real gas decreases as the volume decreases. Now, let us do the pressure correction. Consider a gas molecule in this container. It is surrounded uniformly by other gas molecules from all possible directions. Hence, there is no resultant attractive force on this molecule. So, as the molecule approaches the wall of container, the uniform distribution of molecules around it is disturbed. So, it is attracted by the molecules from the back side only. This is inward pull. So, the molecule with this experience a net inward force by other molecule. So, because of this, the molecule exert pressure as it is striking the wall. So, it will be with lower velocity. Hence, the measured pressure P is less than the ideal pressure. So, it is therefore necessary now to add a correction term, that is P naught, to the measured pressure P in order to obtain the ideal pressure. So, now the equation is P ideal is equal P plus P naught. This pressure correction P naught depends on two factors. First, the frequency of collision with the wall. Second, the force of each collision. Now, both these terms are reduced by the attractive forces which act with a strength proportional to the molar concentration, that is N by V. So, now we can write it mathematically as P naught is directly proportional to N by V into N by V. So, now we can write it as P naught is equal N by V square. So, in place of constant, we can put another constant, that is van der Waals constant. So, now the equation is P naught is equal A into N square by V square. So, now the P ideal is equal P plus A into N square by V square, where A is called the van der Waals constant and it is a correction term for pressure here. Now, let us do the volume correction, because real gas have some volume. Let us consider n number moles of gas placed in a container, its volume is V. If the volume occupied by the molecule themselves is negligible, in that case the space which molecule are free to move, that is equal to capital V. This is the volume of this container. Real gas molecule have volume. If B is the effective volume of 1 mole of gas, in that case for n number of molecules the effective volume or excluded volume is NB. B is the excluded volume here. Now, for an ideal gas, V is equal V, that is the volume of the container's volume is equal to the volume of ideal gas. But in case of real gas, it is not like that. In that case, it is less than the volume of the container. So, now we can write down it V real is equal V minus NB. Here B is called another van der Waals constant and it is correction for the excluded volume. Now, there are two corrections. First is pressure correction. So, now the equation is P ideal is equal P plus A by V square. This is for 1 mole of gas. And second correction is volume correction, that is V ideal is equal V minus B, N is equal 1 here. Here A and B are the pressure and volume correction terms. These both are known as van der Waals constants. By substituting these corrections in ideal gas equation, we get this equation, that is P plus A by V square into V minus B is equal RT. Here P is the pressure, A is the van der Waals constant, V is the volume here and B is the excluded volume. R and T are ideal gas constant and temperature. For 1 mole of gas, N is equal 1, this equation here. Now, let us discuss the significance of van der Waals constant. Let us start with van der Waals constant A. A is measure of intermolecular force of attraction in a gas. Gases which can easily liquefied have larger values of van der Waals constant A. The value of van der Waals constant A increases with ease of liquefaction of the gas. Now, the unit of constant A. A is equal atmosphere liter square per mole square, or we can write it as Newton meter 4 per mole square. Let us discuss the significance of van der Waals constant B. B is the effective volume of the gas molecule. Gases with the smaller values of B will occupy lesser volume. It means the smaller values of B gases will be more compressible because they have very less volume. Now, the unit of van der Waals constant B, that is liter per mole, or we can write it as meter cube per mole. Now, there are some van der Waals constants A and B for some gases. See, there is a table for helium. Van der Waals constant A is 3.46 into 10 to the power minus 3 Pascal meter cube, and van der Waals constant B for helium is 23.1 into 10 to the power minus 6 meter cube per mole. For hydrogen, the van der Waals constant A is 2.45 into 10 to the power minus 2 Pascal meter cube, and van der Waals constant B for hydrogen is 26.6 into 10 to the power minus 6 meter cube per mole. As for carbon dioxide, the van der Waals constant A is 3.96 into 10 to the power minus 1 and the van der Waals constant B is 42.7 into 10 to the power minus 6. So, the value of A is larger for carbon dioxide. It means it can easily liquefy. For helium, the value of B is small. What does it indicate? That it is more compressible because it has lower volume. Now, there is an example for you. For 2 moles of ammonia at 300 Kelvin occupy volume of 5 into 10 to the power minus 3 meter cube. Now, the question is calculate the pressure using van der Waals equation where the values are given for van der Waals constant. A is given, that is 0.417 Newton meter cube per mole square, and B is given, that is 0.037 into 10 to the power minus 3 meter cube per mole. The value of ideal gas constant is R is equal 8.314 Newton meter per Kelvin per mole. Now, the solution is here. The van der Waals equation is P plus A n square by V square into V minus N B is equal R T. From this equation, we can calculate pressure here. So, pressure is equal N R T by V minus N B minus A n square by V square. So, the pressure is given, you can calculate it. The pressure will come 101,266,75 minus 66,720. So, the answer is 945,947 Newton per meter square. So, this is the way you can perform this numerical. In this lecture, we discussed the reason of deviation of real gases. The real gases deviate from ideal character. The reasons were, we did 2 correction in ideal gas equation or in the assumptions of kinetic theory of gases. The real gases were showing maximum variation or maximum deviation at low temperature and high pressure. Then what was the reason? The reason was the distance between the molecule was very less. In that case, they were showing the value of compressibility factor is less than 1 or greater than 1. Then we did 2 corrections in ideal gas equation that was suggested by van der Waals, and we derivate the van der Waals equation. It was P plus A by V square into V minus B is equal R T. After that, we discussed the significance of van der Waals constant A, which is for pressure correction, which directly indicates the pressure or the force of attraction between the gas molecule. If the value of A was larger, in that case it can be easily liquefiable gas. And the B is the van der Waals constant, which indicates the volume. If the volume of B is small, it means compressibility is high. In next lecture, we will derive or we will discuss why excluded volume is not equal to the actual volume of gas, why it is 4 times of actual volume of gas, and then we will discuss or we will check the validity of van der Waals equation. After that, we will discuss or we will derive the Boyle's temperature. Thank you.